This webinar goes over basic SoundCheck sequence writing. First, we're going to talk about how to develop a test, independent of SoundCheck. Then, we'll go over the stimulus, acquisition, and analysis steps, and how to choose different ones. So now, let's look at developing a test. What's the device under test? Really, what are we actually testing? Is this a high-quality speaker that we're going to be listening to music on? Or maybe it's just a smoke detector that should just beep to warn us that something is happening. Depending on what the actual end user scenarios are for this device, it's going to change a lot about how we want to test it and what we care about getting out of it. One other thing that you have to keep in mind, is there any DSP that's going to be filtering out noise or sine waves? That will change how we can approach picking a stimulus to apply to our device under test to get any data out of it. We also need to think about how it connects to the computer. Something like a loudspeaker that can plug into an amplifier, that amplifier can plug into an audio interface, that can plug into a computer via USB. Something like that is a pretty straightforward setup in SoundCheck. We just need to know that we will require an audio interface and an amplifier. But it can get a little bit trickier than that. This could be something that requires Bluetooth. It could be a digital microphone. It could be something that can't connect into the input or output directly. If you're testing a phone speaker or phone microphone, that might not be able to connect directly into SoundCheck. For that, you might need to think about setting up an open loop test. How many channels are needed? For just a single device, we need at minimum one channel for an input. But if I wanted to take multiple tests of the same device, maybe I want the frequency response and impedance of a loudspeaker, I would need two inputs. Or if I had a microphone array, how many inputs I have in that mic array, I would need that many physical inputs. If you're going to be reusing the same station for different types of testing, before you start buying hardware and thinking about how you develop one test, it might be good to think about what the minimum for all devices on that test station would be. If one test needs 4 inputs, but most only need 2, you might be better off buying one 4-input device than just utilizing that for every test, instead of having to switch around between the testing. Is any external power required? Do you need an amplifier, microphone preamp? That's going to be defined by your device under test or what you're using to test it. If your reference microphone needs a preamp, you'll need to get one. Instead of just thinking of the audio interface hardware, there's other hardware that you might need to run your test successfully. Some of it will interface with SoundCheck, but some might not. A head and torso simulator might be needed to get the response of headphones correctly. If you're doing polar measurements, a turntable to actually turn the device around will be required. Additionally, something like a digital I/O to control the logic of the sequence, or a foot switch to start and stop it, might be helpful to set up in your sequence. If that's the case, as you're developing your sequence, it's good to think about how the logic will interface with those pieces of hardware. If you're going to have logic loops because you'll be using a digital I/O, you'll want to think of that from the development stage. You don't want to write out a full test, then have to go back and add in a bunch of things that you weren't thinking about at the start of it. We also need to know what type of environment the test is in. Am I testing this in an anechoic chamber, a production line floor that's really noisy? Am I in the near field, the far field? Where is the device in relation to my testing? What is the noise of the environment it's in? Are there going to be reflections? All of those things are going to dictate what we can use and how much accuracy we can get out of any of our tests. We have to also define what test level to use. This will change depending on what we're actually playing as a stimulus and what our device can actually handle for input. If we're using sine waves, the crest factor of that's going to be a lot different than if we were using pink noise or music. We have to think about how high our peaks can go and where we want our average level throughout our testing. What's our desired accuracy? Accuracy can mean a lot of things. Something like the frequency resolution. If I was using a step sine sweep, do I want to test at R80 or R10? How many frequency points do I want? It could also mean something like noise immunity. Or calibration. If I'm calibrating a microphone before every test, I'm going to have pretty accurate measurements. But that's going to have a hit to my time. It takes time to physically move your reference microphone, put it into a calibrator, and push calibrate. So how often do you want to do that? Do you need to have 0.01 dB of accuracy? If you don't, then you can probably speed up your testing to account for that. You also have to think about the accuracy of your testing components. Transducers will often drift over time, but if you have higher quality test components, they might stay more stable longer. It's something that you'd want to be able to trust if that's what you're using to be calibrated. How much time do you have? If you're on a production line, maybe somebody says I need every device to be tested and moved on within 3 seconds. Or if you're in R&D and they give you a device for 2 weeks and say, tell me X, Y, and Z about this, you can approach writing a sequence in very, very different ways between the two. What's the actual goal for accuracy, and how much of a trade-off do you need to make? If there's no trade-off, you don't need to spend a lot of time thinking about what you're losing. But if there is a real need for speed, you have to think about what you're losing by decreasing the testing time. Because in general, any measurement has some level of uncertainty. The measurement is really only an estimate of what we're inputting to the device versus what we're getting back. If you have more noise, you're going to have more randomness to the level. But longer averaging times can give more accurate results. We answered a couple of questions just simply about the device itself. The real questions when we start developing the sequence are, what are you trying to find out, and what do you already know? If you're testing a device to a standard, it's actually not that difficult to figure out what you need to know. It's laid out in writing what's required to be able to meet this standard. But if you're just trying to pass something to internal or external limits, you might need to discuss with who you're supplying the device to or who's supplying your devices with how to test it and what it means to pass those limits. If you're in the development stage of a project, it might not be limits that you're even trying to meet. It might be limits that you're trying to define yourself. Really, one of the big goals of SoundCheck is to be able to correlate subjective to objective. When you listen to a device, when you hear a recording, listen to a playback, and you think something sounds good, we want to be able to go into SoundCheck and set limits, set up a test that will properly relate what you think is good with a passing result. If there's something that makes the device sound bad, find out what that is in SoundCheck. There's a lot of things we can try and set limits on, types of distortion, and we're really just trying to correlate what sounds good for this particular device with what's acceptable to ship, and then how do we make that show up in software. We don't want to define our product by just a line on the screen. We want to define it by how it sounds and then correlate that to some sort of results. One tip is before you even open up SoundCheck, spend a little bit of time to define what information you'd want on your final report. If you could hand your boss something, or if you could just have a magical printout of everything about the device that you care about, what would be on that? What's required? What's good to have? What's must have? We can take the output from those and then work backwards from here. This chart is straight out of the SoundCheck manual in the analysis chapter. I use this chart a lot when I develop my own tests. What it is showing us on the left side the desired measurement. Then, along the top is all of the analysis algorithms available in SoundCheck. If there's something you need, like frequency response, you can look down that row and see which analysis algorithms will give you that data back. For example, if I know that I need frequency response, non-coherent distortion, and impulse response, then I shouldn't spend a lot of time setting up a sequence using harmonic track as my analysis algorithm, because I know the only thing that can meet those three needs would be transfer function. So I could change how I'm developing my test to work around the analysis type, because I know that analysis type is actually giving me the data I want. This chart's actually printed out and hanging near my desk at work for just a quick reference of when I'm building a sequence from scratch and need to get something done quick without having to go into the algorithm itself and play around too much. I know exactly what I can get with every algorithm. This chart shows us the analysis algorithms with a little bit more detail, showing us what stimuli we can use with them. In my last example, I needed to use transfer function. So I could look at the typical stimulus or read some general application notes, something that's very common to be used with this analysis type. So transfer functions tells me it can be used with program material, and the typical stimulus is noise, speech, or music. So I knew the analysis that I needed to use. I worked backwards, thought about the stimulus that would interface correctly with my analysis algorithm and give me out the data I wanted. This chart is also useful for just a quick overview of common applications. This isn't a fully comprehensive list, it's just some common uses. But if you're looking for a starting point, it can be helpful. If you're testing hearing aids, you could look down this list and see that, okay, broadband and RTA spectrum, those analysis algorithms have something to do with hearing aids. Then you can investigate them more, see what type of stimulus you want to use in your device, and then try and develop a test that way. So there's a couple approaches to how to pick your stimulus and analysis to work together, but they're very closely tied together. When we actually go to create the test in SoundCheck, we have to think of this logically how this sequence would work. So when we start the test, we're choosing the DUT stimulus, something like a sine sweep. We take the stimulus we created and we apply it to our device under test. We compare the response from the device under test to the stimulus we defined in the stimulus step. That analysis is going to give us data like frequency response, phase, distortion. In SoundCheck, we have different categories for those steps. So when we choose the DUT stimulus, in SoundCheck, that's a stimulus step with the STI extension. When we apply the stimulus to the device under test, we call that an acquisition step. And when we compare the stimulus to the recording from the acquisition, it's an analysis type step. And again, these are the core building blocks of how to write a very basic sequence. There's a lot of other steps that are used in SoundCheck, post-processing, limits, displays, that can get us a lot of really good data as well. But in 99% of electroacoustic tests, this is kind of the core of what you're trying to pick. So making sure that these are set up the way that you want them and have the data coming out that you really care about are extremely important. We're going to start going down these lists and look at those three types of steps in SoundCheck in a little bit more detail. Then we'll put them all together and write a test with them. The first step type is stimulus. The stimulus step generates a waveform which then appears in the memory list. Only one waveform is created by any stimulus step. If I needed to create 8 discrete waveforms to be played out of a device at the same time, even though they're playing out at the same time, I would need to set up 8 different stimulus steps to create those in memory. Alternatively, if I had one waveform that I wanted to play out of a speaker in stereo, I could have one stimulus step to define that waveform, then just select it twice on my left and right outputs. But everything that's defined from the stimulus step will only create one waveform. We're skipping over hardware and calibration in this. We're assuming that we know how to set up our physical devices and calibrate them. But it's important to know that when you choose a stimulus step, we're assigning it to a calibration output signal path. Whatever EQ is available on that step, whatever units and the sensitivity are going to be carried over from that calibrated output signal path. If I have a calibrated source speaker and I use that source speaker output path, when I define my stimulus, the level will match the source speaker. So I would be defining it in SPL, and my units and EQ curve would be coming from that source speaker correction. On the other hand, if I chose amplifier channel, then my units would be something like dBV. It's going to be a voltage signal coming out of my amplifier, because that's the calibrated signal path that I choose. And again, the stimulus step doesn't play the stimulus. We can preview it from the step editor, but all the stimulus step does is create it in memory. We take it from memory and then we'll usually apply it in an acquisition step. So all we're doing here is defining what is to be played. This is really flexible and can help us in a couple different ways. But it is important to know that when we're setting up the 3 different types of steps to do one function, we need to make sure they're harmonious. But because they're separate, we can do some different things like open loop testing, testing with multiple types of waveforms, or changing the stimulus on the fly. A new feature in SoundCheck 18 is we can specify the sampling rate to be used inside the stimulus step itself, or simply use the device default. If I'm using an interface that has 10 different sample rates, I could define it in SoundCheck hardware as 44.1. When I ran my sequences and I used device default, the sample rate of my waveform that was created here would be 44.1. But if instead I wanted to test at multiple sample rates within the same sequence, I could create multiple stimulus steps with defined sample rates within them. I could have 44.1, 48, 192. Then as those stimuli are created and ran through acquisition steps, it will change the sample rate of the device to match what was specified in the stimulus step. What I want to do now is go over the different types of stimuli available. We'll look at some pros, some cons, and then the analysis algorithms that'll work with them. The chart we saw before was more from an analysis perspective, but sometimes you want to pick what stimulus you're putting on your device instead. From here, we'll look at why you'd want to use these different types, what features they have that might give you a push in one direction to use them over different types of stimulus, which might then dictate which analysis you can use. The first type is the step sine sweep, also known as Stweep. The pros of this is that it's very easy to specify levels here. I have my frequency range set. I give it a step progression. I can say third octave. I could change this to manually defined by linear or log spacing. I specify how long I'm spending at each of these steps in the step size functionality. So I can really make this do exactly what I want it to do. It's very flexible from that perspective as well. I can specify exactly what I want in a lot of different areas. It also gives good noise immunity. Because we're spending a lot of time at some of these steps, we're able to filter out noise better and give more accurate results. We can get harmonic distortion with this as well. We're stepping between different frequencies. As we're playing out these frequencies, we can use some analysis algorithms to track and filter out the harmonics, compare those to the fundamental, get harmonic distortion out of it. But some of the cons are it can be slow. Because you're spending set amounts of times at each of these steps, you might have to spend a lot of time to reject noise, and it might take a little bit longer to get a test done. It's also not realistic. People aren't buying your products to then listen to sweeps through them. Sine waves are very good for testing, but if you have a device with a lot of DSP on it, maybe you're using a smart speaker or building a laptop that you're trying to filter out any sort of feedback, if you're putting a step sine sweep into that device, the DSP on board might actually change only step sine sweeps and give you back incorrect data for your analysis. Using the Stweep, you can use broadband RMS, heterodyne, and harmonic track algorithms. We'll take a look at the differences between the algorithms a little bit later, but just know that when you use the Stweep, these are the three algorithms that work with it. Next up is the continuous sine sweep, or log TSR. Very similar to the step sine sweep, one of the pros of this is that it's very easy to specify. There's a frequency range, there's a level. I can say what level I want to play across which frequency range. we can get pretty good noise immunity with this. We're also able to get harmonic distortion. We're playing sine waves, we can filter out the harmonics, get back what the harmonic distortion is. This is also the only stimulus that will work to get us simulated free field measurements. It can also be quite fast. The cons, again, are somewhat similar to the step sine sweep. Its frequency resolution, though, isn't quite as straightforward as the step sine sweep, but it's not realistic either. This isn't something that you're going to be playing out of your speakers as you're walking down the street. It's not something that's going to be truly reflecting what end users will be listening to. For this, you need to use the time selective response algorithm. This is what's going to give us those simulated free field measurements. Sine amplitude sweep. Again, very easy to specify, good noise immunity, and we can get harmonic distortion from it. Because the amplitude is sweeping, though, this is really helpful for testing amplitude linearity. What happens in the compressor when it's kicking on a device? If my hearing aid compressor is doing something, if there's some sort of compression in just whatever the DSP is, being able to pick one frequency and then ramping up the level of it can give you some really good data. The cons, though, are it's slow and it's not realistic. For this, we can use broadband RMS, heterodyne, and harmonic track. With the two-tone stimulus type, we have two options for the sweep type. IM is intermodulation, and that will have a master tone that's a step sine sweep, and a slave tone that's a fixed tone. The pros of the IM is that it can give us intermodulation distortion. It's also really helpful for measuring microphone distortion. The reason for this is that measuring distortion on microphones can often be masked by the distortion introduced by your output device. If I'm testing microphone distortion, I'm probably measuring the distortion on my speaker or my mouth that I'm using to test it. But if we use IM sweeps, we could set up one speaker to play the master tone and one speaker to play the slave tone. The harmonic distortion we're getting might still be from those two speakers, but since it's not actually sweeping on the same device, any intermodulation distortion must be coming from the microphone because that's the only thing that's capturing both of them. So if you're struggling to get good distortion measurements on a microphone, try taking a look at using an IM two-tone sweep, see if intermodulation distortion sheds any light that harmonic distortion might be hiding. A con here is that it can be slow, and the analysis algorithm that we'll use is harmonic track. The other two-tone stimulus type is difference. This will have a step sine sweep, and then alongside it, another step sine sweep as the slave tone, with either a fixed frequency difference or a fixed ratio difference. The pros is we can get intermodulation distortion, and it can help keep the distortion products in the passband of the device. But it's slow, it's not particularly useful when looking at even order distortion products, and like all sine tones, it's not very realistic. For this, we have to use the harmonic track analysis algorithm. Multitone will play frequencies between the frequency range specified at the resolution specified as well. The difference between this and a step sine sweep is that all of these frequencies will occur simultaneously. So instead of spending time at 20 hertz and then moving up to the next band, spending time there, it'll just play all of the frequencies at the same time. This is really good because we can get very fast measurements with good noise immunity. It's also really useful for measuring crosstalk. Some cons are there aren't great standards available. This isn't as common as, say, measuring harmonic distortion on a device. So if you find out something about your device under test, trying to compare that apples to apples with some other spec sheets might be a little bit more difficult. And the distortion can be a little bit trickier. We can get distortion out of it, there are options for that, but we can't get harmonic distortion. Since we're playing all these frequencies at the same time, we don't know if the 200 hertz playing is the harmonic caused by 100 hertz, or if it's just the fundamental of 200 hertz. So without being able to filter all of those out and find out what is causing what, the distortion we can get is a little bit different. For the multitone stimulus, you need to use the multitone analysis algorithm. For noise, we have two options that are commonly used, either pink noise or white noise. The pros of this are its high frequency resolution. It also works really good for nth octave spectrum, so using an RTA. Pink noise spectrum is also very similar to music. So this could be something that's a lot closer to the program material that's actually going to be used on your device under test. Instead of just putting sine waves through, it might be good to compare the sine waves as well as looking what happens when you're putting in pink noise. What your device does might be a lot different, and it could be very interesting. The cons, though, is that it does require a lot of averaging because it's noise. It takes more time to settle on to what's caused by the stimulus. Similar to multitone, there's not as many great standards compared to something like harmonic distortion. And we can get distortion products out of it, but it's not harmonic distortion, it's more non-coherence. For this, we can use the FFT spectrum, transfer function, and the RTA spectrum. SoundCheck also allows any wave file to be used as a stimulus. You can point to any file on disk that's a wave file, SoundCheck will read it, play it out in your acquisition steps. For this, we're kind of assuming you're pointing to either music or speech. And the pros for this is that it is realistic. This is what people often will actually be using in their devices, not just similar to it. So it's going to give the best representation of the end result of your device. There's also no issues with speech activity detectors. And a lot of standards will require artificial speech to be used. If you have those standards and have those WAV files, all you need to do in your stimulus step is point to those WAV files and you're able to use them in SoundCheck. Some of the cons, though, is that it does require a lot of averaging and it can be tricky to calibrate level. So even if you just look at this graph on screen right now, we can see that some of the peaks are reaching out to -15. And there's a lot of silence in between because of how speech works. There might be some large difference between the peaks and the RMS values of these. If that's something that you're limited to on the peaks of your output amplification, it could be a little bit harder to pick what level you actually want to use. For this, we can use FFT spectrum, transfer function, and RTA spectrum. This isn't a stimulus type, but it's important to know that you can combine different stimulus types in one stimulus step. We call this a compound stimulus. A really common use case for this would be to combine different resolutions of the same stimulus type. For example, I'm trying to sweep from 20 kilohertz to 20 hertz with a step sine sweep. From 20 kilohertz to 200 hertz, I want my resolution to be R80. But 200 hertz to 20 hertz, I don't care as much, so R10 is fine. I could create a compound stimulus step, have my specified resolution between those different frequency ranges the way I want. Then when it gets put into the memory list, it just comes through as one waveform I could then put in acquisition. We could also put together completely different types of stimulus. In this example, we have a 1K tone before a wave file. With this, we could use this to maybe warm up the device. Maybe there's some sort of DSP or physical properties of the device that when you first start testing might not kick on correctly. So we could put in just some frequencies at the beginning, maybe a quick burst of pink noise just to wake up the device. Or if we're doing open loop testing. Open loop testing often requires a solid sine wave to be able to lock on to do resampling and frequency shifting to make sure that the clocks are aligned between the two devices under test. If we're testing something like speech, we would want to just put a little bit of 1 kilohertz tone or something in the bandpass of your device at the beginning of the stimulus. There's a checkbox in the bottom called Analyze. With Analyze disabled, we're not taking any of that data from that part of the stimulus and using it in the analysis step. So if I ran this stimulus through an RTA spectrum, it would completely ignore the 1K tone at the beginning, which is what I want. I want to use that to just make sure my sequence starts, make sure that my device is playing out some sort of signal. I could use a triggered record looking for 1 kilohertz frequency. But then I want to just kind of throw it away once the recording exists. And by unchecking this box, it gives me a really easy way to do that. The stimulus level and frequency range in a stimulus step, instead of using manually entering in a number like 200 millivolts, you could instead use a memory list item. This allows the parameters to be dynamic and set in the sequence itself. One common example would be to calculate the sensitivity of something at the beginning of a sequence, then using that sensitivity, calculating out what level to play out. Maybe you're trying to find 1 watt through the device. So you calculate using a little bit of a recording at the beginning, find out what the actual level that should be played is, then put that number into the next stimulus for testing. If you've ever calibrated a source speaker, you've also seen this. It will ask you, what level do you want to play out? What frequency range do you want to cover? And those are operator messages that are popping up and asking the user to type in which values to use here. You could have those in your own tests, just telling your operators to plug in what numbers they want to test at. Another option is to set them via TCP/IP. We can define memory list values in the sequence itself, and maybe we're using SoundCheck as just a small part of a huge test suite that runs through 30 different programs. I could take a variable out of program A, put it through an external Python script, then have that variable be plugged into SoundCheck as the upper frequency range of my device. Then when I run my stimulus, that variable is used. SoundCheck will sweep based on that variable. This can be really helpful The one thing to note here is if you ever are using memoryless values, it's going to tell you that you need to disable preload stimulus. This is something that we'll take a look at when we open SoundCheck a little bit later today. But if you ever get that warning, just remember to click on the overall sequence and turn off preload stimulus. That basically means that SoundCheck needs to calculate these values on the fly. It can't put them in memory when the sequence opens, so we need to disable that feature. So using the stimulus step, we've defined the waveform that we want to use for testing. Now, how do we take that and apply it to our device under test? We're going to use an acquisition step. There's three main functions of the acquisition step. The first is playing stimuli from previous steps and simultaneously recording signals on one or more channels. This step type is called a play and record. At once, within one step, we can go out as many signal paths as we want and record in on as many signal paths as we want. There's also a record-only step. We can record on one or more channels without playing any stimulus. Optionally, we can use a trigger here to start recording. For this trigger, we have a few options. We could use just a pure level, so whenever the input exceeds 80 dB SPL, or we could use a level in conjunction with frequency, so whenever it's above 80 dB SPL at 4K, or use an option called cross-correlation. This is using a log sweep with a specified stimulus at the beginning of a compound stimulus that's set to not analyze. Then when SoundCheck sees that exact stimulus in its recording, it will automatically trigger. This makes it for really, really robust and very specific to your sequence ways to trigger. If you've ever tried to do record only in a noisy production line and it triggers off of somebody dropping something or a crank going off, being able to use either frequency-based or chirp-based triggers makes those false triggers a lot easier to get rid of. We can also set up virtual instruments for automated use within the sequence. Anything we can access from the instrument menu, signal generators, multimeters, oscilloscopes, etc. We can add those to a sequence, so as the sequence runs, they'll open up and we can collect data with them. Why would we pick one over the other? So some really common use cases. For acquisition, if we're trying to measure a device's response to a stimulus, then analyze the response. This is the most common use case of an acquisition step. In 95% of electroacoustic testing, we want to use a play and record step. If you're not sure which one you're looking for, pick play and record. You can use this step when the input and output hardware channels can both communicate directly with SoundCheck. So what does that sentence mean? This means that my input and output channels both work fine and can be set up in the hardware editor of SoundCheck. This could be they're both using the same audio interface. Maybe I'm going out of an audio connect, coming back in that same audio connect. Or if my device can connect directly with my computer. If I have a USB headset and I plug my USB headset into my computer, SoundCheck is able to access that device and either input or output from that. Even if you're using Bluetooth, we have Bluetooth devices that will be able to send and receive signals directly from SoundCheck. That will also be able to use a play and record step. Record only we'll need to use when the DUT output cannot communicate directly with SoundCheck. So a really common use for this one would be something like a smart speaker or a cell phone speaker. I can't plug my output of SoundCheck into my phone and make the speaker output my stimulus. What I could do is take my stimulus, save it as a WAV file, put it on my device, and then play it out. When I do that, I could use a record acquisition step to take that data from my external device, bring it into SoundCheck. Then I could go ahead and analyze that versus my stimulus the same way as the play and record step. But again, the key here is when your device under test output can't directly talk to SoundCheck. The other very common use case for this, if you don't have a stimulus to define, if you're just trying to measure the noise of a room or see how isolated something is, you can just record for n seconds, then analyze that recording. Virtual instruments, the use case that's really most common with this is whenever you need something that will update as the sequence runs. When we talked about record only, we said you could record the noise of a room. That's good for just getting the information and then analyzing it for later. But maybe you need to actually do something with that information, and visually seeing it on screen could be helpful. What if I'm trying to tune an active noise cancellation chip? So I want to have a spectrum open as I'm changing the device itself. I want to see how that affects the frequency response. When it meets those limits, I can move on with the sequence. Also very common to confirm the seal on headphones. If you're trying to put headphones on hats, you want to make sure that the seal is what you're expecting. You're not getting a lot of room noise in. We could have a virtual instrument step pop open on screen while you're making those adjustments. When it's within the limits you expect, you move on with the rest of the sequence. You should use this over record only when the syncing input versus output is also not required. With record only, we can take that and analyze it later. With virtual instruments, it's a little bit harder to do that. So I would recommend using virtual instruments when you just want to be able to change things on the fly, and record only when you want to actually analyze it versus something else later. There is one more type of acquisition that we didn't talk about, and it's play only. So similar to record only, we'd want to use this when the input of your device under test can't communicate directly with SoundCheck, like smart speaker microphones or cell phone microphones or anything like that. We define a stimulus, play it out of SoundCheck, and then we could record on our device under test. Then we could take the recording from whatever our device is, copy it back to our computer, and analyze it versus the defined stimulus. Once we're at that point, we can analyze it just like we were doing a play and record step. But there isn't a template for play only. To do this, you can add a play and record acquisition step, then don't pick an input. So it's going to ask you for the output, select what you want there, then when it asks you for an input, just click OK. Alternatively, you could pick an input and then just completely ignore it. But sometimes the play only is a little bit easier than using a signal generator because we can apply our EQ very easily. We can make a lot more definitions on the step beforehand. We can then create it, save it out to disk, do a lot more with it, and automate it within the sequence a little bit easier. When you add in an acquisition step, every input signal path is going to create a max FSD in value in the memory list. This measures signal to noise ratio. We have a recommended scale. We think that the best way to get some good signal to noise on your measurements and make sure you're within an acceptable range is to check the Y value of this max FSD in value and see if it's between minus 30 and 0. If you're under minus 30 dB, your signal to noise ratio is too low. It doesn't mean your measurements aren't good, but it could be one way when you're trying to optimize your measurements to try and get that more within the sweet spot. You could try to increase the input gain. If you have a preamplifier with adjustable gain and your max FSD in value is very low, think about increasing that level. You could increase the stimulus level itself. If you are testing at 80 dB, maybe bring it up to 90 dB. You could decrease the testing distance, move your device under test closer to the source, or try and decrease the room noise. A lot of these are very situational. You'll often not have any say in 3 to 4 of them. Sometimes you just have to take the tests as you come. But if you are trying to develop something, optimize your input gain, take a look at this value. It's something that can help make sure that you're getting the results you expect. On the other hand, if you're above 0 dB, it means the input is clipping. So turn down input gain, pad it, do the opposite of the previous bullet points. If you're using Listen hardware, there's a feature in Acquisition called Auto Range. What this will do is play the signal once, measure the max FSD in of that signal. Then if you have any available input gain that gets within that minus 30 to 0 dB range, it will apply it, then run the test again. For example, Amp Connect has up to 40 dB of input gain. If I ran a test with auto range on, SoundCheck would read my acquisition step and give me back the FSD value. Let's say it was minus 60. It would say, okay, well, I have 40 dB of gain I could add. It would apply that, rerun the acquisition, and give me the new waveform with the higher input gain. If you're not using Listen hardware, or maybe you're on a production line and you don't want to have this happen multiple times, it's best to try and just define this beforehand as you're creating the tests. But if you have the time, if you have Listen hardware, I'd recommend turning this on. So we've defined a waveform with the stimulus step. We've taken the waveform, applied it to our device under test. At this point in time in SoundCheck, we would have two waveforms in the memory list. The stimulus that we defined, then what we actually recorded. In analysis, we're going to compare the two to try and get some data out of them. We've already talked about analysis a little bit, especially that chart at the beginning in the first couple of slides. I highly recommend looking at. It's a very good overview of some of the most common use cases and when to pick some of these. But I just want to go through each of the steps and talk about what they're commonly used for and why you might pick them. Broadband RMS doesn't have any filtering. This is really common in some hearing aid standards. But if you're trying to actually filter out the stimulus versus the noise and make sure you're tracking only what you care about, broadband RMS will be adding more noise than some of the other analysis algorithms. FFT spectrum. Similar to the instrument FFT, we can just feed waveforms into this analysis and get back some noise measurements. Same thing for RTA. RTA, though, will give us nth octave spectrum, which you can define in the analysis step, if it's third octave, sixth octave, etc. The main difference between RTA and FFT, besides the nth octave, is that RTA can also measure frequency response. It takes the recorded waveform spectrum, compares it to the stimulus spectrum, and will give you a frequency response back out of this step. You can turn this off and on inside the step itself. You can specify if you want the stimulus, the recorded time waveform, or frequency response output of this step. This is really common for telephony or devices with DSP. Again, if your signals are being attenuated because they're sine waves, using pink noise or actual speech and music, running that through an RTA spectrum is very common. Heterodyne is used with a step sine sweep stimulus. This will measure the frequency response with tracking filters. Harmonic track is very similar because it will use a step sine sweep stimulus, also measures frequency response with tracking filters, but the big difference between the two is that harmonic track also will measure individual harmonics. Because we're measuring the individual harmonics, we can then get distortion measurements out of this. We can get rub and buzz, we can get THD. This is also where perceptual rub and buzz and IM and DF distortion come into play. So if we're using a two-tone stimulus instead of just the basic step sine sweep, well, we can use harmonic track to get IM and DF distortion out as well. So heterodyne and harmonic track, if you're using step sine sweep, if you only need frequency response, you can pick either of them. But if you need any sort of harmonic distortion, use harmonic track. For a lot of electroacoustic tests, step sine sweep with the harmonic track is very common. Time selective response is used with the log sine sweep for simulated free field measurements. With this, we can also measure frequency response and harmonic distortion. But if you're using simulated free field, if you want simulated free field measurements, you'll need to use the TSR algorithm with the log sine sweep. Multitone is used with the multitone stimulus. So again, if you pick multitone, you have to use multitone. It can give us really fast frequency response measurements. And as we touched on before, we're not getting harmonic distortion out of this, but we can get coherence and non-coherent distortion. So it's very fast and can give us coherence and non-coherent distortion. Very helpful for when we need those parameters. Dual channel or transfer function can be used with any stimulus type, but typically it's with broadband noise or speech. We're measuring the response of the input versus the output. For this, we can get coherence and non-coherent distortion as well. One thing that's really helpful is to use batch analysis. If we have a microphone array with 7 microphones, and we're trying to capture all 7 and compare them to the same stimulus that created them, instead of having one stimulus step with 7 acquisitions and 7 analysis steps, I could create the one stimulus with one acquisition I could record in on all 7 channels. Then I could take those 7 recorded time waveforms, make them a group, and then instead of just pointing to one of those in the analysis step, I could point to the entire group as the response waveform. Whatever algorithm we select is performed on each waveform in that group. So instead of just having frequency response for one, we would have 7 copies of frequency response. One thing to pay attention to here is the data naming options. In the analysis step, under the Curves tab, There are a couple checkboxes for adding in either the signal path or appending it with the data name. To make sure that you know which curve is coming from which waveform, I would recommend turning on one or both of those options. It will just make it a little bit easier to quickly view the memory list and say, curve 3 comes from input 3. Doesn't leave any room for confusion, and it just keeps your data nice and organized. Now we'll look at if I wanted to open up SoundCheck and start doing these things, how would I do them?